Okay, it's an optional question. I just want to point out, I believe it's a difficult question, but looking at the numbers in the problem, I noticed that there's some numbers, they're certainly recognizable trigonometric numbers, and they have something to do with the 60 degree and the 45 degree. All right. So what I did was I wrote a problem down that was related to that, a sum difference formula. All right. So the sum difference formula I'm using over here, I'm using, the sine. Whoops, let's get a pen out. I'm using the sine of a minus b. And what I'm writing down is the sine of, let's see, 60 degrees minus 45 degrees. All right, I convert that to radian, of course. 60 degrees, pi over 180 degrees. That's pi over 3. And the 45 degrees times pi over 180 is going to be pi over 4. All right? That's all I did over here. All right? And the sine, a minus b, the sine of a, cosine of b, sine of b, cosine of a. And I evaluate that. And again, you'd need to know two triangles for that. You would need to know the 60-degree triangle, and that was going to be root 3, 2, 1. And you need to know the 45-degree right triangle, 1, 1, root 2. All right? So I write it down. The sine of pi over 3, that's root 3 over 2. And the cosine of 45 degrees is 1 over root 2, or if you rationalize the denominator, root 2 over 2. The sine of 45 degrees, again, is 1 over root 2, but if you rationalize it, root 2 over 2. And the cosine of pi over 3 is 1/2, all right? The next thing is I factored this out from those two terms, and we left off with root 3 minus 1, all right? And again, this is equal to, pi over 3 minus, the sine of pi over 3 minus pi over 4. Let me get my eraser out, and what I'm going to do now is I want to emphasize that, 60 minus 45 is actually 15 degrees. All right, so we got the sine of 15 degrees, all right? Now, 15 degrees also, you can look at it as, instead of the 60, pi over 3 minus pi over 4. And that's the sine. And that's the sine of, well, if you take pi over 3, a little more complicated, pi over 4, you get common denominator 12, and you get 4 minus 3, which is 1, so pi over 12. All right? So it's really the same thing as sine pi over 12. And what I did then was I saw this as the sine of pi over 12 is equal to root 2 over 4 times root 3 minus 1. Then I multiply both sides by 4 divided by root 2. Write that down, 4 divided by root 2 sine pi over 12 is equal root 3 minus 1. I'm going to rationalize that too by multiplying top and bottom by root 2. And what would you get? You would get 2 root 2 sine pi over 12 equals root 3 minus 1. All right, so we went through that derivation. We got this over here. All right, I'm going to say that's done. I understand that. So why would you have done that? I see that in the problem. All right, I'm going to get my eraser out and emphasize that you're at an important milestone in the problem. All right, now certainly it worked well on the first term. It's going to work well in the second term. And the second term, what I wrote down was, I'll get a little better at this. I wrote this one down, all right, very related to this one over here. Cosine, maybe I should write that down for you. So the cosine of a minus b. Cosine a, cosine b, plus sine a, sine b. All right, let's write that down. We're writing this over here. And we just went through those evaluations before, so it's really not that difficult. Cosine of pi over 3 is 1/2. The cosine of pi over 4, root 2 over 2. The sine of pi over 3, root 3 over 2. Sine of pi over 4. And then what do I factor that again? And really the same, nonsense I did before. I solve for root 3 plus 1. All right? So what I have now is, to go back to the original equation, I just plug those in. All right? The next thing I would probably do is I would probably divide both sides by 2 root 2. Relatively simple to do. What do you get on the right side? You get 2. Well, on the left side, those 2 root 2's disappear, so you get this over here, all right? The next thing I would do is probably multiply both sides by the LCD, all right? And if you did that, you know, the LCD, let me write that down for you. The LCD, whoops, is sine x times cosine x. So what are you going to get? You get this over here, and then you get, well, let's take a look. Well, the sine would cancel off. You get the cosine x. What would cancel off the cosine? You get the sine of x, all right? I recognize this, again, as a sum formula. All right, it's important you recognize sum formula. And I'm seeing this now as almost being a trivial problem, but it's not, all right? So I'm seeing this over here. Whoops. And I'm seeing their arguments have to be equal, certainly, right? So pi over 12. But unfortunately, the trigonometric functions are periodic, and there's a concern over here about what other solutions there might be. And if you subtract x from both sides, you get pi over 12 is equal to x. I call this a trivial solution, by the way. It's the easiest one to come up with. And certainly, we're dealing with sines and cosines, and this would repeat itself over and over again, all right? And it's something you should be very familiar with at this point, all right? Now, granted, what I'm going to talk about now is I'm going to try to figure out other solutions to the problem. And I got to look at cases. And the problem with looking at cases, you might be confused by the cases. But the first case is where both the angles, the x plus 15 and the 2x, are in the first quadrant. And certainly under those conditions, you know, the reference angle is just x plus 15 and 2x. And I know the signs have the same sign there, so I just set the arguments equal. And I get that first solution. All right, let's talk about the next case. The next case where this, the first angle is between 0 and 90, but then I put the next angle, which is twice x, into the second quadrant. And you should realize that they both will evaluate to the same number, all right? And they're both positive, by the way. So what I do is I put the reference down. Well, the reference for the x plus 15 degrees in the first quadrant is x plus 15 degrees. But the 2x now in the second quadrant, so what's going to be the reference, I'll write this over here, reference angle, that's what we're looking at, is 180 degrees minus 2x. So I set them equal to one another, all right, the references. And I solve, and I get this over here, and I convert to radian measure, all right? And again, that's relatively simple to do. The problem is, as things move forward, they get a little more, you know, I'm not saying they're more difficult, but it's kind of hard to understand what's going on over here. The next thing I want to do is I want to put the angle x plus 15 into the third quadrant, and that's where the sign becomes negative. And then I'm going to throw the other angle into the fourth quadrant, and also the sign there is negative. But I got to get the reference angle. So let's talk about the reference angle in the first one. The first angle here, the reference angle there. Well, I'll just say the first reference angle. Well, it's going to be, let's see, let's take a look. It's x plus 15 is in the third quadrant. So I've got to take the x plus 15, I want to make the reference over here, and subtract away 180. So the reference there, x minus 165 degrees. Let me outline where that is, right over here. Now the next guy, I'll call it reference number 2, is in the third quadrant. So what's that going to be? It's going to be, let's see, 360 degrees minus the 2x. All right, I'm using degrees because it's easier for me to handle that, at least writing it and typesetting it. So let's write that down. So the references would have to be equal. So, you know, x minus 165, that reference would have to equal this reference over here. And that's pretty simple to solve. What do you get? 175 degrees, and then they convert it to radian measure. All right? Now, case number 4, and I always say the wheel's going to bus go round and round. We got to keep moving this thing. And I'm moving it, what I'm going to move it to, I'm going to move the angle into the, you know, again, what I mean by this, we've already done this. We've gone this way, and I'm over here, and that quadrant over there. And now I'm going to be moving it, let's say the first angle. Let's go, let me erase that. The first angle I had, right, it was between 270 and the last one I did was between 180 and 270, so over here somewhere. And now what I'm going to do is continue on, and I'm going to move it into here, all right? And what would that be? Actually, I don't want to move it there. Let me just, that's too far to move it, all right? I want to make it negative. Whoops. So it was here. I'm going to move it over here, all right? So I'm going to say the x plus 15 now is between 270 and 360. Now, but remember, I did the other one. I had to move the other one forward too. Now, I'm going to move it forward to, let's take a look. It was here. It was negative there. Whoops. And I want to keep moving it. I'm going to be moving it over here now. Whoops, not there. Over here. I want to make it negative again. And what would that be? Let's take a look at that. 360, 450. Let me say 360, 450, 540. All right? So it'll be between 540 and then over here, add another 90 onto that, 630. All right? So I got the references again. All right? Let's get my eraser out, and we'll talk reference. So the x plus 15, the reference for that, we'll talk the first one. Let's see, it's going to be, let's see, 360 degrees minus this, so minus x minus 15 degrees, which is 345 degrees minus x. All right, I got the reference there. All right, let's do the other one. What's the other one going to be? Let's take a look. That's going to be in the, let's see, I got to do this, so I got to be careful with this. It's going to be 2x minus 540 degrees, and that's theta R2. Let's see if we got that written down right over here. And then I solve it, and yeah, it's a fairly easy equation to solve, by the way. You'll get this over here, convert it to radian, all right? I also provide a graph for you to help visualize those solutions, by the way. So let's take a look at the graph, and the graph's over here, and we're expecting to see 4 points of intersection here, 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 and here. And to write the degree measures down for those, let's just talk about that. The first degree measure I get is 15 degrees. So this is 15 degrees. The degree measure over here will be the next one I found, which was 55 degrees. So I'll get my eraser out here. The next measure we found was 175 degrees. And the next measure I found was that 295, and I'll put this over here. All right, let me just go through the values over here. This value over here is 180 degrees. This value over here is 360 degrees. I'm just putting in degrees, by the way. What am I getting over here? Well, this over here is 90 degrees, and I'm just looking at the sine curve over here. This is 270 degrees. I think you get the idea. And so forth and so on, 45 degrees over here, so forth and so on. And again, someone says, why do you put a graph down? Just to, reaffirm my belief in the numbers I'm getting are good numbers, all right? And again, these are partial graphs. This repeats itself over and over again on a cycle, since we're doing sines and cosines 2 pi. Thank you.